Hello, everyone. Welcome to Practical GCP. So I've been trying to use DeepSeek version 2 as a drop-in replacement for ChatGPT since it came out late December until now. So that's almost the whole month, right, on a daily basis. I've not looked back since. So recently, just a couple of days ago, DeepSeek has released a new model called R1, which is open source and is very, very strong on reasoning, just like ChatGPT O1, right? So it's one of these models can give it some thoughts before it gives you the answer. And this is specifically good for coding, for example. And open source means you can run it yourself, right? But what's always been challenging is how do you run these very capable open source models without going through all the complexity to set it up with all that deployment hustles. Plus, it usually has a very high cost on GPU, right? So today, what I want to do is to show you what I've done, aiming for a much simpler production-ready setup using Cloud Run, right? And combined with the DeepSeek R1 model. So let's crack on. So to start with, I want to do a quick introduction of the three key things we'll cover in today's session. So the first one is Cloud Run with GPU support. Not long ago, Cloud Run has added this new feature that you can now attach a single GPU to each Cloud Run instance. So the choice is quite limited at the moment. Is the Nvidia L4 GPU you can use at the moment, but it's still quite powerful. And the proof is now you can actually run the DeepSeek R1 7 billion model, and I will show you what it's actually capable of doing with that model today. And the reason I picked this one is because one is quite new, and two is very powerful. It is something that people use to compare with the ChatGPT O1 model at a similar level of quality, specifically on reasoning, such as very complex coding tasks, right? So Ollama, lastly, is the thing that I'm using to wrap around. Is basically a wrapper that you can actually use to deploy, to run those models that you don't actually have to go through all that complex setup. But one thing that I don't really see anyone doing is to actually have a production setup using this. So that's why I wanted to try it, and I'll see how good it is, do some performance testing, scalability testing to see what it can give me. And I'm quite excited to show you what I've done. Right, I'll give you a quick overview of what we'll cover today. So there's quite a few parts I want to talk about. First of all, I want to show you some design considerations. So why should you care? So if you have the, let's say, ChatGPT or even the DeepSeek API you can use directly, why would you bother running open source, right? So this is one of the things I want to show you in the design. And also, what would you use it for, right? That's all these things will cover in the design with a few simple things in a diagram. Secondly, I want to go through the packaging and deployment. As I mentioned, there is a very simple way to do this now with Cloud Run, but it still requires a bit of work. But I'll show you the solution I went with and why did I do that. Right. So performance and scalability is one of the key things to cover, because I really want to understand how good is it, right? So how many concurrent sessions can I run in a single Cloud Run instance, right? How do I scale it? Does it auto scale the GPUs, right? Because I've not actually seen that before myself. So I want to test all of these variations and then show that to you. Then I want to do a bit of cost analysis, because cost is always the very important thing when you actually run any production solutions. You want to know, based on the use cases you cover for your business, how much is actually going to cost you based on the specific thing you want to develop. Right? I'll give you some examples in there, and finally, I'll go through, in my view, what are some of the key benefits and why should you really care running such as DeepSeek in Cloud Run yourself, right? Instead of using the other alternatives. Right, let's look at the design. So this design is pretty simple, and that's what we want actually, which is great. So basically what's happening here is you can see on the left, you've got this Cloud Run API backend that is servicing your web applications, your mobile applications, and your internal applications, let's say enterprise apps that inside your business that you built, because there's the Gen AI models, such as the reasoning models, especially for coding, there's lots of ways you can use it. So it's not just the B2C use cases, but also within the business with the B2B use cases. So they can be very, very powerful for to deploy those yourself. But the way I want to design this specifically in this case is you don't really want to mix up your application and the model itself. So the design here is very clearly putting two Cloud Run instances here, right? So if you have an application backend, keep that separate, and then the DeepSeek the model you deploy would have an API that you can call, which you can expose. I'll show you how that actually works through the Ollama Cloud Run interface, right? With the REST APIs, then you can actually call that through the Cloud Run to Cloud Run integration. So the things that with this area here is that so the container is so the container is packaged using the DeepSeek model, right? And then the key thing with this design is you can see here what I've illustrated is you can attach the Nvidia L4 GPU to each Cloud Run instance, which has DeepSeek running on it. But the key thing in there is actually you can actually auto scale it, right? And that includes auto scaling to 0, right? There's no standing charge. So let's say in the evenings, especially for the applications not very busy, in the off-peak times, you don't have to have any results running. This is the key thing, and this is why this thing is amazing, right? So with all the other options I see so far, you can't actually scale to 0. This is not possible. But this one, you can actually scale to 0, but you can also scale to 100 or whatever, right? In this sense. So the GPU would auto scale alongside with based on your workload. So I'll show you this in the demo as well. But this is the most important reason why it's such a simple solution, but at the same time, it's extremely powerful as well. Okay, next, let's look at packaging and deployment. As I mentioned, it's a very simple process, but I'll walk you through it on some of the complexity and comparisons on why I prefer this way to deploy, right? So first of all, it's better, in my view, to use the Docker file to package it. So you've got the Ollama wrapper, you've got the Docker file, you've got the DeepSeek model. Package it all together is a few lines of code. It's in the repo that I shared. And then all you have to do is to use Cloud Build to package the container and then save as image, push it to artifact registry, right? There is a interesting thing here is, as you can see, I've mentioned the model, the DeepSeek model is cached in the container image. So what this means is when you build the DeepSeek model, what you can do is you can download the whole DeepSeek model, which is about 5 gigabytes, and then you actually put that whole thing because when you run Ollama, you don't actually have any model, so it's very lightweight. But if you actually put DeepSeek in it, it's actually really significantly increased the size of the container image. So, but I prefer this way, and I'm going to explain in a second why. And when you push to artifacts registry, you can now deploy that to Cloud Run, right? So once it's deployed, you run something like this. You can use the API. There's also a CLI tool, which is more interactive. It's actually very good for testing. But for production use cases where Cloud Run can serve traffic, then you can use this HTTPS endpoint, right? So the thing here is you can basically use the API generate to reference the name of the model, and then you can give it a prompt, and that will return the results to you, just like ChatGPT, right? There's a number of endpoints. The API documentation on Ollama is actually really, really good. So this is a more complex version of the streaming endpoint with API generate, but there's also another chat version that I think is more lightweight that will give you the less response. But this one will include many other things, including the statistics as well, right? But there is something being mentioned in the Google documentation such that there are a number of ways that you can deploy. And one thing it did say was this way of my choice to deploy could cause problems of cold start, right? So, but based on what I've tested, you can see I've done a screenshot in here as well based on what I evaluated on the cold start time. So the container startup latency, from what I can see, is only 4 to 6 seconds. So keep in mind, now I've actually downloaded the entire DeepSeek model into the container image, which makes the image about 5 GB big, right? That's pretty large image. But the thing is now because DeepSeek is downloaded already into the artifacts registry image, when you're using it, you don't have to deal with any downloading or moving from other places anymore, right? So this is all managed by Cloud Run with that container. So it deal with that yourself. So I thought if this is really slow, I'll replace it. But 4 to 6 second cold start time when it triggers the scaling isn't actually a big deal for me. I think, at least from my perspective, because if you think about the way the LLM works, it's not like you have hundreds of thousands of requests hitting something that needs millisecond latency, right? This thing is a streaming interactive feedback. So the 4 to 6 seconds cold start latency, which only triggers when it scales up, is not a problem, right? And also, I think the other main reason I want to do this is because you've actually put it into artifacts registry, and when you deploy it, the model is already downloaded in the container image. That means you don't need internet, right? You can remove internet in your deployment, so everything is securely locked down into your VPC environment, right? So there are a little bit of downside though, but I think it can be ignored. One is you need to use a slightly larger instance. So this one is the high CPU one because the model is quite big and it does take a bit of time to build. And because it has the extended duration, I think it's about 6 minutes, and it took to build this. So it's not bad, but it still took 6 minutes. I think for a smaller one, it might take a lot shorter, like a minute, right? But I think this is worth it because of the very little cold start time and the kind of workload with LLMs. I think this is with a minimal complexity, and that's the way I would prefer. Okay, now I would like to give you a demo to show exactly what I've done. The one thing I really wanted is to see is how auto scaling affects the scalability and the performance. Because when you have lots of users hitting your endpoint, you do have to be able to scale up. So one of the key things I wanted to check was, does it actually work? Does it actually get better? What about latencies? What about other things? So now after the demo, I'll give you a more detailed review on the performance optimization I tried and the different variations. So I think it'll be more interesting after you see the demo. So what you're seeing here is something I've just done in the code to send 30 concurrent requests to the Cloud Run service. So what's happening here is, and the specific thing I wanted to see is when you see this is when it was idle, right? There's nothing there. I ran many things like before, but right now I've got nothing. And then one of the key things, because I expect to see, is to see auto scaling immediately. Right? When I ask the model something, I expect it to scale up to the 3 active instances as I set it to, which it did, right? Because I've only given, if you look at the concurrency here, to 5. So immediately you can see this hits 5 concurrent requests, and then it started dropping because the request started getting processed, queued, and then goes down, right? Because I sent 30, and it clearly can't handle it. I think after the demo, I'll do a deep analysis on the optimization I tried, on what worked, what didn't work, so you can see it in there. But in the demo, you can see I've actually got 3 containers, and it's scaled up from 0. So this was like no stats, and then it just jumped straight into from 2 and to 0. And now because there's no traffic come through, so it's kind of dropping down, right? So there's a few important things to look at. The thing that's most interesting is the GPU utilization. So when I send it 30 requests, you can see immediately this is jumped into utilization close to 90%, right? And even with the scaling up of the containers, it still stayed really high until the request was processed and it went down. However, when it comes down to the GPU memory usage or utilization, it all stayed pretty low. So in this case, it was only 25%, right? In addition, the container memory utilization, so this is like a memory attached with the CPU, you can see the CPU utilization was less than 30%, and then the memory utilization was around 30%. So it's actually not utilized, even the GPU is almost packed, right? So, and also, as I mentioned, the container startup latency was very low. So you see the maximum was 4.8 seconds, and then it dropped to lower as well. But this typically stays around 5 seconds. It's not high, as I mentioned. I don't think it's a problem, right? So the request latency, as you can see in here, what's happening here is that you typically, as you start giving more requests, if it can't handle, the latency will increase. But one thing to distinguish this with your normal applications is that keep in mind that this is a streaming use case. So what that means is, let's say if I give it a relatively complex Airflow question, right? Give me write a DAG, but consider A and B and C, for example. It's going to take a while to think about it, right? And it's going to generate a bunch of code for me, and this is going to take time. I find this for these complex questions, and it takes time to think. Typically, it takes 1 minute and 1 minute half, so like 90 seconds to 100 seconds, right? You can see this, because I sent it too much, and it has to auto scale, and it started kind of struggling a little bit, and then that's why it started queuing up. That's why the latency increases. So later on, I will do a optimization to show you how do you actually reduce that latency and what is the optimum setup, right? So this is another dashboard I've created. It's just easier to see what is going on here. And later on, I'll use another complicated one to show you what I've done in the comparison of cost, and specifically on the utilization of the resources. All right. So yeah, so you can see here the concurrent request was high and it dropped into low. Most interestingly is again the GPU utilization, right? So this is what's going on in here in the demo. What I also want to show you is this container build time. You remember that thing I said is going to cache a pretty big container in here. So, and that's because it has to download everything here and install the container, download all of this stuff, and then eventually package it and upload it. This is like a 5 gigabytes, I think. That's why you have to use a bigger machine, because it's heavier and then it takes a bit of time to build it and then push it. But like I said, the benefit is very clear, and you don't have to download it at runtime. This is an all build time scenario, right? And when you actually go to the Cloud Run instance, right, this is the one I've deployed. I want to cover a few important things in here. And one of them is the resources on CPU and memory. So you cannot use less than 4 CPUs or less than 16 gigs. So if you try that, it will tell you there's no such thing, right? Because it won't be able to complement the Nvidia L4 GPU if you do that, which is interesting because the CPU and memory are heavily underutilized in this particular case. So, but it's currently in preview, and here you can attach the GPU, and you can only attach one, which kind of makes sense. But I think if you can't utilize this CPU and memory, either reduce this to half, right, to have the best tuning. I don't know what is the overhead, or something that you really need 4 and 16, but you all give this to 2, right? And then you can actually use one container to handle more requests, right? The other thing is here, right? The maximum concurrent requests. So later on, again, I'm going to show you what is the optimum setting you want to do this, because you do want things to to trigger the up and downs, right? That's what you want to do, because otherwise it's going to either queue up for so long, can't handle request, it won't scale up, it's going to cause a lot of problems. The last thing that I want to cover in the settings is the variables. There's 3 environment variables I set. This is all documented in the Ollama documentation on optimizing primarily the caching mechanism for when you give one session multiple prompts, right? That's when you say ask one question, you go to second one and third one, and that's what some of these things would help, because you will increase the parallelization a little bit for those kind of things, and it also turn on the KV, the key value cache, so which helps to optimize the memory usage, right? So those are the optimum settings I found. But feel free to let me know what you found and then what you used the tuning mechanism that helped more, especially if you found a way to help with the concurrency. Yeah, that's pretty much on this side. So what I also want to show you what it actually looks like from the other side when you're actually triggering the Ollama command line and also Ollama APIs, right? Because at the end of the day, you want to use another application or user interface to call this model and give you a response. So first of all, there's a very easy way to test it, because I realized that quite a lot of you probably don't know this, is to use something like this. So this is a Cloud Run service proxy. So what this means is you can attach this to an existing running Cloud Run service and tunnel the port, right, to your local host. So if you run this, you can see what it says in there. So first of all, you need to choose. I need to pass this in the variables. It's easier. My one is running on, because this is only where it's available in Europe, is 21, which is Europe West 4. And what's going to happen is now the DeepSeek model container now is mapped into my localhost at port 9090 via a proxy to the Ollama DeepSeek R1B model running on Cloud Run, right? So you see, this is interesting because now I can issue requests to 9090 on my localhost to test exactly what's going on. So first, I'm going to show you the CLI. You can use the Ollama host as a environment variable to pass your localhost 9090 to Ollama run DeepSeek model, right? So what this is going to do is to open up like a chat window. Right now, you can talk to it. So I think I ran this for a while. So now now there's a little bit of code start. So let's wait for 4 to 6 seconds, which is you see 4 to 6 seconds. Now the GPU and the container is up. So you can ask a relatively complex question to see how it responds, right? So let's say write an Airflow DAG based on you are using Composer 3, Cloud Composer 3, and only use the Python operator to get data CSV, right? CSV data from GCS bucket, right? In GS blah files star, right? Let's see what it does. So you see, it's very quickly responding to me, and it started doing the think part, right? So this is exactly like the OM model is going to think about what I'm asking about. You see, this is asking, okay, I'm talking about the GCS file, right? I'm talking about minimum airflow has a GS operator. It actually look at all of this stuff and think about it before giving me an answer. This is why it's going to take that 1 minute, whatever, right? And then it's going to start writing all of these things, right? So I think, yeah, you can see it's doing a pretty good job already. So this is what the model is really good at, because it can actually see the details and then kind of give you a much better response. So here you get the response, right? Now I can ask again, right? Okay, just give me the code. Code and don't think too much, right? Something like that. Then it's going to keep responding to me. So this CLI, right? Although I'm seeing you just showing the CLI, I've got an example here as well. So here, I'm using an easy one, but it's the same thing, right? With the API generate, this gives you a bit more complex response versus API chat, but this is all in the Ollama documentation. If you run this, you can see this is exactly what's happening behind the scenes. Is streamed all of the results, right? Based on all of these outcomes is produced in the response. Yeah, all the way. And this is something that you can now use in your application side. You want it to stream and then do whatever you need to do, right? So once it's finished, at the end, it will give you a summary with the statistics, which is because this is the verbose version, but you also have the non-verbose version in the chat, right? This is it, right? I just want to show you what it looks like, because without seeing it, you probably don't know. Okay, is this similar to ChatGPT? But at the end of the day, it's just an API with streaming enabled, and then you can actually test it exactly the same thing, right? So here, there you go. Okay, now you've seen the demo, so you can see the auto scaling works, and you can also see I've actually done quite a lot of things to test the performance. I'm not going to show you all of the details on different variations I've tested, but instead I'm going to summarize what I've done and the outcome I've seen with those testing I've done, right? So what I wanted to do is to test the performance and scalability primarily to see what can it handle, right? Because it's a quite large model. It's a 6 billion model and is a reasoning model, which is quite slow and it's very GPU heavy. So I was quite skeptical, does it even run, right? So, and then I put these test cases together and then run some concurrency tests to see if it's able to produce good results with good response time if I give it something relatively complex, right? It's not just a hello world, right? Something a bit more like, in this case, I've actually variations. I want to, as an input, give it 10 to 30 real world like data engineering questions based on Airflow and Composer 3 prompts, right? So such as write an Airflow task to validate the schema of some sort of file type stored in the storage, like before processing. So I want to see what kind of, because this usually gives you relatively long answers, and it takes a bit of time to do that. If you have quite a lot of concurrency, I want to see, while all of these are long running tasks and streaming things, what would happen, right? So this is something I wanted to check. And The other thing that I've given it is based on the single Cloud Run instance with 4 CPU, 16 gig of RAM. I want to also see if there's any actually impact on the CPU and RAM, but it actually turns out there isn't. So I'm going to tell you that first. So that I'm not going to focus on that because it has no impact whatsoever. And the CPU and RAM are always underutilized in the GPU setup. But this is the main game here is the Nvidia L4 GPU. It's only equipped with one. Why does it equip with one? Because it has auto scaling. There's no point giving you two, right? If you need more, just go up. Right. So the other thing is now I want to do some adjustments. So I want to see if I give it different Cloud Run instance level concurrencies, ranging from, 5, 10, 30. I want to see exactly how does that affect things on the other side, which is the Ollama optimization options. So there's quite a lot of things I've done in there. So I will show you a table in the upcoming page that you see what I actually mean by optimization options. What I want to evaluate as an outcome is one, how does these settings affect concurrency and latency? Because one thing I'm trying to see is not only it can scale up, which we already saw in the demo, but also what I want to see is there some ways that I can actually optimize the concurrency, right? Such as, there's a thing called context caching. There's a number of things I've played with. I want to see if these things actually affect concurrency as well, rather than just the single chat session. So that's something I want to play around with to see if there's any performance gains in there or any GPU optimized output, so I can actually put more concurrent queries in there. So, and then lastly is how many requests can one Cloud Run instance handle as an optimum setup based on all of these tests I've done. Right, so here it is. This is the optimization attempts I've done. It might look a bit overwhelming, but basically what I'm trying to do is I did 9 runs, right? So from number 1 to number 9, that's the 9 runs I did. For each run, I'm giving it from 10 requests to 15 to 30, and then drop down to 15 and 10 and 5. So the reason I did this was that initially this is kind of following my instinct and so what might happen, right? And then I want to say, look, if I give it 10 requests, which is not a lot based on what I read, this is probably already quite a lot for the Nvidia L4 GPU to handle, and it turns out it was. So, but I was like, I did a number of adjustment. So, for example, I increased the Ollama number of parallelization after reading. Well, you can increase a little bit, right? So I've actually tried to increase a little bit just to see whether it's actually helping me or not. The reason I did that was because I noticed that although the GPU utilization was quite high, but the GPU memory utilization was quite low. So I was wondering if there's a way I can actually increase the parallelization to make the RAM gets used more, right? So somehow to get more concurrency out of it. And then there's some other things I've adjusted based on the request concurrency. So request concurrency is the parameter you set at the instance level for max number of requests you allow before it scale up. So this one is the one I send. This is the one it allows. So this is the maximum, right? So if I send 16, one will get dropped or scale up the instance. So this one here is the quantization is basically a way that you can turn it on. Then it should technically reduce the memory footprint or memory usage, basically make it more efficient, right? But I think because I read two different kind of version of this, and one says it will only improve. This is what Ollama says. It will only improve the single session like memory efficiency and the GPU compute efficiency. So if you turn this on, right? But there's another version saying, look, if you turn this on, it will also help you with your concurrency because the between the sessions, right, in different sessions. Right? I was just want to see if that's true or not. And then the last one is around the different kind of cache levels. So in a nutshell, F16 is the default, which is the highest setting when you turn this on. But then if you change to Q80, which will actually half the memory footprint for the single session version, but at the same time, it will have a slightly reduction on the quality of the output. So I didn't want to tune it down too much, right? So this is just the, let me try to see if it helps. And then you probably see what happened because the test you can see is kind of started going down, right? So now let me show you the actual outcome. This is more interesting. So it's not exactly good news. I'll explain this bits by bits. You can see this is the 9 test we did, right, with kind of different variations. So if you look at the first one, the first group, so 1 and 2 and 3, just to remind you, these are the ones I've sent 10 requests, concurrent requests, right? And then 3 is 15 concurrent requests with relatively low parallelization on the Ollama side, right? So you can see here we are already getting with 10 to 15 requests into 4 minutes latency. So the 4 minutes latency is the latency of the P95s. In this case, I used the P95 for majority of the requests to return that didn't have too much of a delay, right? So I look at the context token length for return. So basically, in terms of return, it usually takes about a minute or a bit more, maybe a minute and a half for the longest resource to be returned by the model. So 4 minutes means there's quite a bit of model in the queue, right? That means there's no way the one GPU can handle that many requests. That's the short answer, right? But then you actually get into the 4 and 5 and 6. So this is where it gets interesting, right? The 4 and 5 and 6, this is where I increase the request from 15 to 30. I've also, in the process of trying to turn on the caching as well, right? I've trying to turn on the caching as well. The interesting thing here is it still has a significant increase, right? Like 50% increase on the latency, right? This basically means, again, it cannot handle the 30 request, right? It's not too bad, but it cannot handle the 30 request. So even with all of that optimization, which I increased concurrency, the parallelization settings on the Ollama side, but one thing interesting you want to see, that you probably already noticed, is the GPU utilization, even from the very start, has been very high. And I think I mentioned briefly in a few slides away that I said the reason I want to test this out is the memory utilization has not been very high. So if you look at the memory utilization, it's only been like in here is like 30%, right? I was like, is there a way that it can cache some of this stuff in memory? And when it started processing things, it will use less GPU, some clever caching. But again, the thing is, it won't be able to do clever caching because all of these requests, they are in different sessions, right? So I'm sending all of this in different sessions. It's not the same session asking more and more questions. So the caching on the model side, on the Ollama model, with the model side would help, but it won't help concurrency between sessions. So that's what I've seen in here, right? So, but what I've also seen is that, look, because the GPU utilization is very high, I can't really get the memory utilization up to make sense of doing anything, right? If you actually don't care about response, you can actually do more of these because you can see the jump is actually not 100%, right? It's not doubled. So there's still some performance gains in there by putting more things in there. Um, However, the problem is that a lot of these would have been queued, right? Would have been queued. And the issue is if you have, a B2C or B2B app that there's a human on the other side using your thing, you can't really do that, right? Because they're literally sit there and waiting, and that's not very good. So what I've figured out is the optimum is actually by, you see, the GPU usage is still very high, even when I reduce this to 5 requests per container, right? So I only send 5 requests per container. I reset all of this to the optimum, which has 8 parallelization and with caching turned on, and the GPU still goes up to like 80%. But the concurrency you see in here with the latency, it goes up to 1 minute. So this is about exactly, right. It means there's no queue going on in there, right? So this is probably the optimum setting. And basically, in conclusion, I've got 3 things here, is that optimization has very little impact to optimize concurrency, right? So I've not spent too much time testing the turns, right? If you have one prompt in the same session, then you have a second and third, which I think that caching would help, because that's what it says in the documentation, that's specifically what it's for, right? I haven't tested too much, but you can try it out. But it does not have an impact on concurrency. This is the main thing I care about, because I want to scale. Right? I want to auto scale to see how many can handle. Then I can work out how many users I can serve in an application setting. The other thing is the 5 concurrent requests around 5 feels like the optimum setup for one instance, no matter what you do. Right? That's the second thing I found out. And then I think any attempts to increase requests beyond 5 seems to have a major impact on latency. So this jump was like 50%, 100% jump in traffic, resulted in around 50%, right, increase in latency, which is not great, not bad, too bad either. But if you're already kind of in this pattern with 4 to 6 minutes, which typically each user feedback takes about a minute and a half, right, to see that all streaming output to return, you're literally talking about a very bad user experience. So I wouldn't recommend go beyond that. But that's just the things I saw. I don't know if there's any other smarter optimization you can do for this kind of instances, but so far, this based on my spend like 2 days on this. This is pretty much all I can see, right? So let's do a bit of cost analysis. This is the good news, right? So you can see I pulled out the billing dashboard out here with how many seconds I've used. This is from yesterday's statistics. And then I've also got the the CPU allocation. The reason this number is much higher is because I've got 4 cores, right, attached to each instance. You can see the couple of hours of time in here costed £1.67. So I converted everything to dollars. It's just easier for everyone watching the video to understand. So based on this cost, I worked out the cost is combined cost per GPU plus CPU hour, because the CPU is also required, although CPU and memory is always about like 20 to 40%. It never goes up, right? That's it. It cannot use them. So it's a bit of wasted. I don't know why, but you can't actually allocate any less CPUs in this particular case. It's not allowed. It won't give you that option, right? But the combined cost per GPU and CPU hour is $1.23, right? It's actually pretty low, right? If you look at it in the sense that if you're assuming each GPU or Cloud Run instance can serve 5 concurrent requests, which is what I saw previously with very complicated data engineering questions, you still have to think, right? Don't forget that it has to kind of go and think about it and then come back to you. So it's very complex request. You can handle 5 of them. So let's say you spend 2 hours, right? I mean, I don't know how many hours you guys use every day, because you can't always just do ChatGPT, right, all day long. Let's say you do 2 out of your 8-hour working day, right? That's already plenty. So 2 hours, let's say this is the minimum you spend per day on this model. And that works out a cost of estimate per user per day is only less than 50 cents, right? This is per user per day. And that works out per month, which excluding weekend, and that makes sense. You're talking about less than $10 per user per month, which is cheaper than ChatGPT API. Well, I wouldn't say API, but cheaper than ChatGPT, the O1 model. And this one, the good thing is if you actually use it more, use it less, it's all up to you to control, right? You don't have to pay that. I think in the UI you have to pay $200 for unlimited use of the O1 model. And this one you can actually control yourself and do how much you want to spend, right? This is not like that. I did look at the ChatGPT API for that includes the O1 model. It's ridiculously expensive. It's not this kind of price, right? So I think it's definitely worth checking out to see what this looks like to you. But if you think in the sense that if you build a B2B app or B2C app, this is actually very tangible, right? Because the cost in here is per month based on this average usage of 2 hours is less than $10. So it's not like completely unreasonable, but keep in mind this is the OM model as well, right? There's other models specifically designed for coding, which is much more lightweight. I haven't tested this out, but you can actually with the lightweight model, you can actually serve a lot more than 5 concurrent requests per node. That means the cost will reduce, right? Okay, and lastly, I want to talk about the key benefits, right? So we talk about all of this stuff. So why should you care? It's a bit of a summary, but also more importantly, let's look at this in the holistic view on why using Cloud Run with GPU to run this is important. I think we all would agree this is very easy to implement. It's not much at all. So I figured out a little bit the harder bit, but the rest is very simple and straightforward setup. No complicated things for you to deal with. There's no outgoing internet traffic. I think this is very important, especially combined with the way that I cached the DeepSeek model in the container image. It makes the container image bigger, but it's actually a very secure way to deal with it because you don't need internet when you run it, right? And that's very important. And if you deploy yourself, and then you can also improve the output with your own data. So this is where you build more complex applications. Let's say this is why I use this container as just a dumb container that you can use other Cloud Run other Cloud Run services or jobs to call the API in let's say the DeepSeek Cloud Run container, right? So what that means is you can actually make this a very sophisticated application by using DeepSeek or other models that deployed into different containers to build very sophisticated applications using this Cloud Run deployment with the GPU attached, right? And the key thing is because this doesn't actually send your data to a third party, everything is stayed in your own cloud environment, right? Because this is the beauty of open source models. You can actually do this yourself without too much pain, without too much worrying about your privacy issues as well. So cost control, you can set and manage the budgets easily, but also, like I said, it's actually very cheap compared to, think about O1 is a very strong reasoning model. So does DeepSeek R1, right? So it's a 7 billion model, and you can actually run 5 of them to 5 users in a single Cloud Run instance, right? So this is actually ridiculous if you just think about it. How can you even do that, right? So a few months ago, we talking about O1 is amazing. You can never run it. Right now, you're running the reasoning model like O1 with the same score in a single Cloud Run container with 5 concurrent requests, right? This is ridiculous. This is really exciting. And the last thing I think is important as well, right? So if you think about efficiency improvements, although, as I mentioned, I couldn't figure out much more ways to do some clever caching to improve concurrency based on the same, GPU instance per instance. And I think this is primarily because the O1 is very expensive. So does the R1, right? It is using a lot of the compute power. And funny enough, I actually try to turn off the GPU to see what actually happens, and it can't even process a single request in a container, and it takes ridiculous a long time to stream word to word to me. It was just so slow, right? So this is actually a very heavy computational model in there. So, but the reason I want to talk about the last point with the caching options is that if you think about the type of applications you build, right? So think in the sense that if you build some applications that a lot of the results could be similar, right? The results could be similar. When you take turns, you can actually cache what's been previously asked and what the results being returned in a clever way in, let's say, a document database, or in a database that supports a vector index, right? So I support a vector search. So what that means is you can actually create very sophisticated applications to cache the prompt to reduce the cost even further, and then cache the results of the prompt, right? And you can actually compare the similarity of the the prompt that people are asking, all the results, because you can store these in a vector database to do it in there instead of doing it here. Because using GPU is very, very expensive to always get LLMs to calculate everything. But if you actually have popular answers, the similar answers that you don't actually always have to hit the GPU or the Cloud Run service, you can actually return the cached version, right? So just be careful, don't mix up different users things. So although if you run a generic application, it's fine, but if it's session based per user, you don't really want to mix that up because it could be confidential information the user is asking. If you mix the sessions up, and you'll be a huge problem, right? You can do that, but it's quite complex, but the options are there, right? Okay, I think that's, at least I was very excited because I've been following this model a lot, and this is the first open source model that is, lightweight enough for you to run something like this, and it's actually decent with a very, very high score. So I'm actually very interested in this, but more interestingly, what I'm mostly interested in is the way that you can use Cloud Run and GPUs to do this sort of deployment at ease. There's not much to do at all, right? So I've actually tested quite a lot of the auto scaling, running for more than 24 hours now, and I'm not actually seeing any issues. But I really want to see how this can be potentially used in production, in a production setup. Start with something small within your organization, but because this is such a secure setup, and you can actually combine it with many other things, right? That you never have to ask permissions to say, hey, I need to enable this IP API, I need to buy this, I need to do procurement. No such thing. You run this in your own environment. It's just a Docker container, push to an image, cache it, and then off you go, right? Hope this is useful. Yeah, very exciting stuff. I'll see you next time.